French capital of Alps, so there are very nice mountains around. So if you like hiking, that's an ideal city to live in. It's a small city, less than 500,000 inhabitants. And if you like physics, solid phase physics, that's also the place to be. French
Grenoble and
capital
Paris
of Alps,
are
so
two
there are
biggest
very
centers
nice
of
mountains
physics
around.
So
in
so
the
if you
French
like
capital of
that's
Alps,
an ideal.
so there are very nice city to live in.
Scientific
Peninsula, so if you like hiking,
see the
that's an ideal.
ring.
And if you like physics,
You can
solid
see
phase
as well
physics,
here the
that's
nuclear
also
reactor.
the place to
So
be.
these are the big facilities.
French
Grenoble and
capital of
Paris
Alps,
are
so
two
we are
biggest
the
centers
small
of
big
physics.
facilities. So in
So
the
if you
French
like
capital
capital,
of
that's
Alps
an ideal.
National,
There are very nice
Peninsula,
cities to live
magnetic
around.
field lab. And we are specialized in the DC field. We're the same lab as here in the Hefei. There is a high field lab. We are the oldest lab. In Hefei is the youngest lab of that type. There is also in Toulouse for pulsed field. So we are doing the NMR. So this, to explain a little bit the title, the low energy spin excitation translates to the NMR quantity, which is the relaxation rate. So we are measuring relaxation rate, and this is directly reflecting the low energy spin dynamics. We'll see a little bit why. The second type, the critical, has two meanings here. It can be, you know, that the one-dimensional systems are critical with respect to they order at zero temperature, do not order, they are critical with respect to that. Correlation functions are the power law. The same is for two-dimensional systems. They are critical with respect to the Kostelis-Taulas transition, which is not a zero temperature, but it's also an exotic type of a transition. So in low D systems, we have a criticality. And when we go from when we change the phase at zero temperature, then we have a quantum critical point. So then we can speak of quantum critical point criticality. So we'll address all this criticality in the BEC-type antiferromagnets. We'll see what it is a little bit. So first, I'd like to start with presenting the group. The NMR group at the High Field Lab was founded by the late Claude Berthier. Here are the permanent members. High TC superconductors, that was Tau's subject, and it still is. It's run by Marc-Henri Julien. The other exotic superconducting state like FFLO are mostly covered by Adrien Maillafre. Stefan Kramer is trying to make a higher resolution in the resistive magnet, which is difficult. And so he's working in the paramagnetic relaxation enhancement in contrast agents for MRI. So that's his theme. And myself and our very young youngest collaborators, Igor Vinograd, we are in the quantum magnetism, where I covered mainly three different subjects. One is the magnetization plateaus, already an old subject, a spin nematic phase that is a more recent subject, and in this talk I will address the subject of Bose-Einstein condensation, or rather the study of the quasi-1D or quasi-2D systems that Bose-Einstein condensed at low temperature. For quasi-1Ds, they are described by Tomonaga-Lattinger liquid theory. And my main collaborator in quasi-1D, that's Martin Kleinček from Ljubljana, Slovenia. And for theory, it's Edmond Aurignac from Lyon, France. For a quasi-2D system, it's Ragnit, which is my former postdoc. And for theory is Nicolas Lafrancy from Toulouse. And I must not forget many other collaborators, in particular sample growers, because we do not grow our samples, and then many other theories, which good NMR collaborations, a little bit less PhD students and postdocs than here. I see many. Okay. Now, the NMR in one slide, just to define what I measure. So very short. The NMR, what we do in the NMR, we use the magnetic moment of the nucleus, which is a very nicely calibrated moment, to measure the field at the nuclear position. So we measure roughly at that object, we measure the frequency, and the frequency is very precise in measure. So we know it's very precise. So the story goes, we put the system in the external magnetic field. The system, say, polarizes some spins, so some spins are polarized, and these polarized spins will create additional spin on top of the applied spin. So that we measure total field, which is external plus the induced spin, and this one directly is proportional to the spin. So if we have temperature-induced variation, change in the frequency will directly show us the change in the spin value. So spin value is NMR frequency. Okay. Then the other quantities, it's not only the value, but we can measure directly the spin fluctuations. And that's the quantity that we will discuss in this talk. So the formula is like that. I will not tell you how to measure, but this is the object that we measure. We measure the transverse fluctuation of this local field. So that means transverse fluctuations of these spins, mainly transverse, but if the coupling is non-diagonal, then also the longitudinal fluctuations. And then, but Fourier transform at the very, very low frequency, so that we measure actually in the zero energy limit. So this is important because this is compatible with the description of TLL. TLL is a low energy description, and we exactly measure the spin fluctuations in the low energy. Okay, we make it a little bit complicated. If the coupling is not to one spin, but to several spin, and typically we write everything in the Q space. So these correlator are calculated by the theories. By the theories, they are always calculated in the Q space. And then we have to integrate over the Q space. So that's the object theorists will calculate, and they know how to calculate it. And then we measure directly that the same object. And then the same formula that you will see most often is when you apply to this fluctuation dissipation theorem, then instead of that, you get imaginary part of the susceptibility divided by frequency. And that, so we measure the dynamic part, absorption of the system. Here, that's this hyperfine coupling, which can depend on Q, but for us, it will be Q independent. It will be just a constant and just a simple. So here, I'd like to show you how this looks in a real life. And that's for fun. I mean, it is to show that's Professor Wei Chang. Okay, it's a little bit old, but he was there and he was measuring. So the resistive magnet is pretty big. Here it's in the basement, you see. The injected current, there are huge current leads which inject the current inside. And if you inject 20 megawatts in, it's a resistive. It's not, you generate heat by 20 megawatt. You need to cool it down. So these are tubes for the cooling water. So it's a huge installation to inject 20 megawatts and to cool it down at the same time so that there are no problems. For the NMR, the disadvantage is that these are ordinary magnets. So these magnets are meant to produce high field. They are not meant to be homogeneous as for NMR is required. So we have to know how to do the NMR in the ordinary magnet. So in this NMR magnet, you see that's a basement, and on the ground floor, that's here is dilution refrigerator cryostat, and you can see the top loading probe, and you can also see one of our visitors doing manual tuning and matching. This is now automatic, so this is outdated. Here there is no more guides run by the, and we still do that. We were the first one to run the dilution refrigerator at high fields for the NMR, and we are still doing that. So here you can see the recent experiment 1.5 months ago, 29 Tesla, and that's Igor Vinograd who is running. Homemade spectrometer, very good characteristics. Then that's the console to drive the magnetic field. and the Oxford dilution refrigerator pumping group to run the dilution refrigerator. So that's how it looks. One important information is that when you submit a project, we are open to visitors. Any visitors can come. When your project is accepted, you get 1 week of measurement, roughly 6 hours per day. So you get only 40 and something, a little bit more than 40 hours of magnet time. This is not much for the NMR. We typically need more, so it's essential to be very well prepared, to do everything before in the low fields, to know what to do, and then you are focused, and then you can get results in only 1 week. Okay, so a little bit the system. So the system, what we look at the compounds that are actually Mott insulators, so that they are represented only by the electronic spin degree of freedom, and we are looking for the most simple one, Heisenberg Hamiltonian. So we have only spin-dot-spin interaction in the magnetic field, and hopefully nothing else, because everything else will give other problems. And then everything is in the geometry, how these spins are coupled between each other. So for the pedagogical reason, we will here discuss mostly antiferromagnetic spin system. So let's see how it works for a collection of spin 1/2 dimers. Dimers is a pair of spin. If you take a pair of spin 1/2, then that's the energy diagram. Okay, so you have a spin pair in a singlet state. There is a triplet state, which is Zeeman split, and one of the polarized states will go below, becomes the ground states at the high field, at the critical field. So for these spin pair, if we forget about these two states in a Hilbert space, we focus on these two states. So these two states will be our hardcore bosons for the theorist. So, and then we combine these dimers in a certain geometry to make the object that we study. So the most simple geometry is one-dimensional. So you take dimers and you make one-dimensional objects. So this is a ladder. Okay? So when you make these dimers interact, so these are the interaction exchange. So what happens is these energy levels for the two spins becomes bands. So these two states are cut not on at one critical field, but they have two critical fields, and the magnetic field is increasing continuously the boson density, or the magnon density, if you wish. The magnetization is increased continuously between the two critical fields. We have a gapped regime, linearly closing of the gap, linear open of the gap. We have a gapless regime where the magnetization increase, and by a field we control precisely how much magnetization we want in. So we have a field control boson density, so which makes that our system is sort of a quasi 1D bosonic metal. So in fermion world, it's very difficult to change the density. You make it, it's difficult. But here in the boson world, it's very easy to change the density. We can make it, we just change the field. So in this system, that's a measurement in one system. We see the magnetization measured by the NMR. At about 6.5 Tesla, magnetization starts. And at about 14 Tesla, the system is fully polarized. The magnetization has this shape, which is Arcus cosine, which is a signature of the 1D behavior. Okay. So if we put on top of that the temperature, so then the phase diagram becomes like that. So we don't look at one ladder. In a real compound, there are many ladders, and there is a small 3D interaction between them. So if we cool down the temperature below the 3D interaction, the system will, in the end, finally order in antiferromagnetic order. So this antiferromagnetic order, as it is the order made of bosons, can be described as a Bose-Einstein condensation. So this is why we call the system BEC systems. And there are many systems. You can see there is a review article already 10 years old, where you can see many systems where always the low field BEC phase has this dome-shaped. So, and if we are above this phase, this zone is where the system is gapless. So we have a one-dimensional gapless system, which means that it can be described as a Tomonaga-Lattinger liquid. Okay? And it is surrounded by two quantum critical points, because here even at 0 temperature we change from ordered to the state without the order. So what we will measure? It's very simple. We will measure our T1 as a function of temperature and see how much information we can get out of it. So for 1D system, it will be 1D critical or 2D critical. We can measure it at the quantum critical point, and then we will get a quantum critical behavior. We can also measure it as a function of field. It's technically more difficult, but it can also bring a very simple information that describes the system. Okay, now, so an example, final example, what do we get out of it? We take a one-dimensional system, so here it's Ising-like spin chain compound, Bakovo, and we measure like this. We measure from the high temperature into the phase. So we measure this object, which are the spin fluctuations. So this is a second order phase transition, we have critical spin fluctuations. Critical spin fluctuations are seen directly as a peak of our quantity, which measures these fluctuations. So the peak is the position of the phase transition. That's a 3D ordering. So around the phase transition, the fluctuations are 3D critical. Okay? But 3D critical fluctuations are very narrow. If we go high above the transition, we are in the one-dimensional regime. One-dimensional regime means that the correlators are a power law, which means that our spin fluctuation is a power law, log-log scale, straight line. Okay? And these are the pure 1D critical fluctuations. That means that with respect to the theoretical 0 temperature transition. But as we have a real system, it turns out that these fluctuations, because the system is not real 1D, it's quasi 1D, these fluctuations have a big tail which extends like that. And it turns out actually that we can precisely describe our data if on top of the TLL description, which is pure one-dimensional, we put RPA correction. Okay? And then the theoretical formula describes perfectly the fit. Okay? RPA, I will remind you, is as simple as that. You take 1D susceptibility and you add the denominator, which is 1 plus Q-dependent coupling times the same susceptibility. Yeah? That's the RPA. And how we know that it works? But we know that it works because we do the fit experimentally, it works. But then, before that, theorists have calculated this correction, which is here the small points, small diamond points, and they have compared that from the quantum Monte Carlo result. Quantum Monte Carlo is meant to be exact. RPA is approximation. And then we see that the dots overlie, so the theory, the approximation, and the quantum Monte Carlo, they fit together. And we see that the theory and the experimental points fit together. So we know that it works. Now, so what do? We have the relaxation rate. We have a purely 1D behavior, which is a power law, and there is a factor, which is the RPA correction. And it turns out that this RPA correction just depends on the interaction parameter, K, and the temperature. So interaction, I will remind you, if you describe any gapless 1D system in a Tomanaga-Latinger liquid description, you have an effective Hamiltonian which has only two parameters. One parameter is a renormalized Fermi velocity, u, and the other parameter is k. That's the interaction parameter. That's the one here. So that is the one that we can measure. And here, these correction functions, we have a pretty, we can calculate that. So, and we see, so that's as a function of temperature and as a function of k. Interaction 1 means no interaction. Smaller numbers are repulsive interaction. Bigger numbers are attractive interaction. So we see that this correction factor only weakly depends on the correlation. It mostly describes the temperature-induced correction. And we see that it starts to be negligible, but as far as 3 times Tc. So, and we see another thing, that this correction is not very big. So here very close to a transition, and it's only a factor of 2. Now, you will surely say that this is a horrible formula, and this is what I said. You have, it's difficult to program that. You can, it's not that difficult. But you can, as an experimentalist, you can calculate the formula by yourself. It's not that difficult. So this is, I would just like to say, you take a book for 1 dimensions, you have the 1-dimensional susceptibility given in the book. That these are just product of 2 beta functions. So if you, for calculated T1, if you just take 1D, you integrate that over Q, you get this power law dependence. This dependence converts to that. If you want to add the RPA, so this is the RPA expression, you look for the imaginary part of that, and you inject that, you arrange this integral into this form, and then you read out what is your phi function. And you get your phi function as a 3D integral of the Q space, and you see that it's only depends on the K. You see that this is a temperature dependence, that it's only temperature dependent, which you see explicitly here, and the K is here and here also. And there is something else. Here is the geometry of the 3-dimensional coupling. So it's a normalized geometry of the 3-dimensional transverse coupling. So, which means that numerically, it's very easy to calculate that. It's not at all complicated. This is the whole program to calculate that. You write that object, which is a product of 2 beta functions. You find imaginary part, you find the real part, you write this integral. This is the whole program, which means that you can calculate it, even being an experimentalist, for any geometry of the coupling. So here it's the previous, that was calculated for the tetragonal system. But here, for example, there's the orthorhombic. So in y direction and x direction, there is some anisotropy. The message is that you have a control for any type of couplings, and you have a full description. Now, explanation a little bit, what is the K parameter in the affair, interaction parameter? So the best example for this is that if we take spin ladders, so this is the case that we discussed. We have a strong coupling along the rung, and which is weakly coupled along the legs. And what we did, we look at this element. So this is a 0-dimensional element, and out of a 0-dimensional element, we make 1-dimensional object. But you can have, for a spin ladder, you can have the other type of coupling. Let's imagine that the coupling is strong here along the leg and weak here. So if you have this ladder, you cannot select one 0-dimensional object that is used to make the whole object. This is fundamentally 1-dimensional. So you see that these 2 types of coupling for the same geometry are fundamentally different. you see that it's obvious that they are different. And the consequence is that these objects, whenever it's made of the dimer systems, when they are described as a fermion or bosons, in 1D is the same, they lead to a repulsive coupling, K less than 1. And these ladders will give attractive coupling, which is K bigger than 1. And this has been calculated by the theorists quite some time ago, and they calculated the K value for the ladders for any ratio of the two couplings that we see here. And so we see for these couplings, we see that K value, as we increase the magnetization, their variable is magnetization. Our variable would be a magnetic field within the first and the second critical field. We see that the K goes from the non-interacting 1 value, then it goes lower, and it goes back to the non-interacting value. For this type of system, it goes up. Okay? So we can see that the system behaves quite differently. And the point is that we can see that in the NMR. We can measure the relaxation above this phase, let's say at 2 times the temperature, as a function of the field. And then the one-dimensional formula will give you this as a function of the K, and the K depends on the magnetization. So, and then if we measure that as a function of the field, we can see a prediction by this formula for the attractive case, and we see that we reproduce this shape in the temperature, in the field dependence of the relaxation. So we get a concave dependence, and for the attractive system, we get convex dependence. So simply by measuring how T1 depends on the magnetic field from the critical field, if it goes up or if it goes down, we know what is the nature of the, so even if we don't know what it is, how it is configured, we know the nature of the system. So that's the advantage here, and that gives you the feeling of the difference, what it is, the K factor. Now, here is the example. We go back to the temperature dependence, and here in this spin ladder system, we measured as a function of the magnetic field. And as a function of the magnetic field, theorists have calculated the interaction parameter, and that's a black curve. Okay? We fit our NMR data with the TLL plus the RPA, so the red is the color code, and we get the numerical values which sit on the theoretical value. And the message is that if you try to fit that by a pure power law, so you say, okay, here it's rather a power law, I will fit these data. Okay, you fit this data, but the problem is that this is a long tail. So if you fit this data, the slope will not be a good one. You get the points which behave similarly, but they are numerically they are wrong. So you need to apply the RPA correction to get the good description, and out from the data to get the good K value. And there is another remark also, that at the critical field, the TLL description is not valid. Then that you do not get a good fit with that. But that's normal because the TLL intrinsically the constraints are not fulfilled when you are close to the critical field. Okay. Now we go back to this. This is, so that was that was the Heisenberg system. So if we go back, this is quite another nature, Ising-like chain, and so we have a nice fit, but more importantly, here the K value is close to 1/4, and this is what is expected. And if we go to the high field, so this system saturates above 21 Tesla. So going from 20 Tesla to 21, K goes from 0.9 to 1. So we see that we recover the theoretically expected value. So we really get the fine description of that. And finally, I told you that we can calculate this correction for any geometry. So if we go from the tetragonal black line and we reduce the coupling in one direction to get an orthorhombic system, there is an increase in the fluctuation. But it's not that big. It's just a factor of 2. And we understand this because here we are reducing the dimensions. We have, when in one direction the coupling is 0, we have a one dimension in 2 dimension. Reduced dimensions are always increasing the fluctuation. We can calculate it for the hexagonal system as well, and for the ferromagnetic, which is not frustrated, the fluctuation goes down because we have more neighbors. We have 6 neighbors and not 4. But hexagonal is frustrated. Frustrated system has more fluctuations. We have more. So the point is that for one system, we know everything for any system. And why is that important? Because then, knowing how it behaves in 1D, we can look at the other system. And the idea is to approach the 2-dimensional systems. So here is the example. The peak, this is relatively small peak. So in 1 dimension, you have a relatively small peak of the relaxation. You go to 2 dimension, you have a big peak, which is near, that's 1 order of magnitude. But you still have a big tail in 2 dimensions. If you go to the 3 dimensions, then there is no tail. You have only very localized sharp peak. 3D critical fluctuations are localized in temperature. So just by looking of how the peak of fluctuation looks like, you can see whether the system is quasi-1-dimensional, quasi-2, or 3-dimensional. So that's one advantage on the qualitative level. On a quantitative level, in 2 dimensions, the description, 2D critical description is that the T1 should be again a power law, but a power law in the correlation length. And the correlation length should have this dependence, where this is Kosterlitz-Towler's temperature. The point is that you can always fit the behavior using this function if you take this as a parameter, free parameter, and this as a free parameter. You can always fit, but you never know this is the good value, because you cannot measure. This is the value, the system, this is the temperature where the system would order if you cut out the 3D correlation. You take a system that's a 3D system, it 3D orders, but if you just cut one plane of the same system, then that would be that you cannot measure that. So our idea was to approach to see how we can fit that by the quantum Monte Carlo simulation to get control over this parameter. If you get reliable control of this parameter, you can get reliable critical values.
So here you think it's a KT transition here for this 2D system?
For the real 2D system is the KT transition.
Because I remember you say it's an E thing.
The real system is always quasi 2D, okay. So you have a transition slightly above. Okay, so in a real system you have a transition, you have a nail temperature transition, and then this is a transition. This is the temperature where the transition would be if you cut the 3D couplings to 0 for an ideal plane of the same system, but just one plane. So, okay. So the issue is looking for the ideal system. So what we wanted to see is what we would like to have is the ideal tetragonal system of dimers. So there has been a holy grail experimental, and there was a system, by the way, called Han purple, which is very well known in China, I think, the color called Han purple. Unfortunately, this system consisted of layers of that, but in the real system, the layers were not the same. So the system was complicated. And inside of the layer, there was incommensurate order. So the system was hoped to be ideal. It was not. And the problem was how to make it normal. And there were some tricks to make it normal. And one of the tricks was to add the chlorine. So to look for the modified Ham purple. This is the structure. So the essential element which has, these are the copper is carrying spin 1/2. So this is a pair of spin 1/2. So these planes are essentially the same in the two compounds, but there are chlorines here. This makes the system homogeneous. It's not really tetragonal, it's slightly orthorhombic, which means that the exchanges in two directions are slightly different. But this is not a major effect. It's something, this is not harmful to the physics. The magnetization measurement, the curves, so that's the magnetization, that's the derivative to make, to see, it's very well two-dimensional. So the hope was that this was the system. And what is more important in that is, so this is the phase boundary of the system. The red points are measured by the NMR. The whole system is contained between 13 and 28.5 Tesla. So this is 2 times, the fields are here 2 times smaller than in this compound. But it also means that we can measure much more easily, because if you multiply this by 2, you are towards 50 Tesla, and you no longer have a DC field. So this is very convenient compound. So for us, this is ideal compound where we try to learn things. So first, in this compound, what do we measure? We measure this again as a function of temperature. And the first, what we see is the peak. So the peak is the critical fluctuations, and this defines the phase boundary. So the phase boundary here, it's at low fields given by the dilution fridge measurements, at high fields by the helium-3 measurements. These are the red points. And with quantum Monte Carlo, we have a simulation of this system. And you see that blue diamonds here. So the quantum Monte Carlo simulation nicely overlapped the shape of the dome. So we know that our simulation is reliable. We are reliably recovering the shape of the experimental shape of the low end of the BEC phase. But when we know that, so these are the 3D quantum Monte Carlo. So instead of 3D quantum Monte Carlo, you just cut one plane instead of having many. And then you can calculate where is the BKT temperature. So for the same parameters, you can see where is the BKT. You just kill 3D and you take the one plane, 2D, and you can calculate the shape of the Kosterlitz-Towles transition. So once you know the Kosterlitz-Towles, you can also calculate then the ratio between the two. So and you see that here it's pretty flat. So it's the Kosterlitz in this system, the Kosterlitz-Towles temperature is about 30% less than the 3D ordering temperature. So the advantage is that after this procedure, we know as a function of the magnetic field what this parameter is. It's no longer a fit parameter. It's the parameter which is deduced from the description of the system. Okay. Now, then, what we further can do with quantum Monte Carlo, which is much more difficult, we can calculate the T1 fluctuation, relaxation rate, and this is always done as a function of Q. So as a function of the wave vector, you get something that in the contour plot looks like that. So this is a unit cell. So these are the peaks, and this is the pit inside the peaks. And then what I did here, I have enlarged a little bit the space to 4 unit cell, and I cut a unit cell in another way. to have the peak and the other part all in the same. And then you can make a 3D representation of this Q dependence. And you see that at low temperature, you have a narrow peak. So the fluctuations are localized around the antiferromagnetic wave vector. As you go to higher temperature, this peak is broadened and broadened. And what is interesting here, in fact, you can nicely fit this peak almost to the end. And the fit is very simple. It's actually a simple exponential fit, meaning that, and the coefficient then gives you directly the psi, the correlation length. Okay, the peak is never the exponent should linearly cut here to 0. So we have something which has a flat top. So we add a little bit, there's a gap-like function which simulates the flat top. But this part of the curve is precisely the exponential behavior. You have square root of psi square, okay? So which is just the simple exponential. So we can do this simulation. We can calculate the psi from the T1 simulation. We can calculate the psi from the standard quantum Monte Carlo. And we see that these points overlap. So these here, this line, these are the points which are all for the two-dimensional systems. So in two-dimension, we can go to the systems which are quite big, and we see the behavior. And here, one of these points is also the three-dimensional fit. So in this case, we can also make a simulation. So the system was 32 times 8 sites. The points are magenta point, and we see that the psi that is obtained is the same as in 2 dimensions. Is the same, and just close to the nail transition, the three-dimensional fluctuations come in and increase additionally there. So we see the effect of the 3D fluctuations close to the real transition. Otherwise, this curve is nicely described by the theoretical curve up to this value of psi. After the value of psi, which is about 1.5 to 1 to 2. So, and that is normal. The critical behavior for the psi value is valid for big values of psi correlation length, but not for the small ones. So the theoretical formula, we know which is the temperature range where our 2D description is valid, and and we know that it is the 2D descriptions is valid even in the real quasi two-dimensional case. So, and then we know the correspondence between the two. So once we know the correspondence between the temperature and the correlation length, we can convert our temperature dependent spin fluctuations data. We can convert this scale to the correlation length scale. We use simply this critical formula, and we know that this critical formula, 2D critical, is valid here close to a transition. And as a surprise, that these curves which are here apart, they fell on each other, in fact. So the dependence is here. We have the dependence is power law, a straight line in a log-log scale, and it is essential dependence is through the critical coefficient. There is not much field dependence. All the dependence is through the correlation length, and then so that knows that we know everything about the correlation length, so we can establish the critical behavior, and we can measure the critical exponent by the NMR, and it's 1.2. So we get a reliable information about that quantity. Now, so So now let's see how we can compare what is good and what is bad, the situation that we have between the NMR and the quantum Monte Carlo simulation. One very good thing is that if we go to the critical field is where the BEC phase ends. So this is here at 28 Tesla. We measure the data, red dots here. You see very weak temperature dependence. We calculate the data by quantum Monte Carlo for the 3D system. We have a perfect agreement. So we have an agreement between the temperature dependence between the NMR and the quantum Monte Carlo at the critical field. So this is, and the exponent is very small. So this we know, this is very nice. If we look at the NMR data, this converted to the dependence on the correlation length, we know that here NMR experiment gives us the exponent 1.2. But if we calculate the quantum Monte Carlo, the peak is much smaller. If we fit the Xi dependence over the quantum Monte Carlo data, we get the exponent which is very small, which is 0.4, 3 times smaller than the quantum Monte Carlo, than the NMR result. So currently we have a problem of we don't understand why this mismatch between the experiment and so quantum Monte Carlo is missing some fluctuation. Is the NMR response enhanced from some reason? There are no logical reasons for that would be enhanced, that would enhance the NMR data. Also, the exponent, the NMR exponent is 1.2. So normally, this exponent is dynamical exponent minus eta. Eta should be 1/4. So for the diffusive spin-spin correlations, Z is 2, exponent should be 1.75. For a ballistic, that's energy conserving correlation, should be 1. So these two numbers is here, the value is in between the two. So we still do not have a full understanding of the mismatch between the quantum Monte Carlo simulations and the NMR experiment. So the subject is well localized, well described, but still we need, it's a challenge for the theorists to proceed.
So the material is layered, or it's just it's kind of 3D material?
Yeah.
It's a 3D material.
All the experimental materials are 3D.
Do you have any estimation about the layer coupling? Because if they're coupling between layers, you can correct it.
No, but these simulations are, these are, sorry. If you see, excuse me. So these simulations, the quantum Monte Carlo simulations, excuse me, you see, quantum Monte Carlo, here the simulations for the critical field, you see it's 32 times 8. So it's a 3D quantum Monte Carlo. So it's not the issue of 3D, 2D. So we have a full description for quantum Monte Carlo in 3 dimensions, and we still have some mismatch between the quantum QMC and the NMR. Okay?
Yeah, but at a quantum critical point, they agree, right? So this power is minus.
Yes. Here this agrees, but out of that point it does not agree. So that is the issue. So here the temperature dependence agree. So that allows you to match the two scales. But if you match the scales here, the absolute value here, prediction quantum Monte Carlo is much lower than the NMR, and the exponent is much lower than the experimental. So this remains to be understood. And these are already old data, but we are just about to write the, we thought that we would understand it theoretically, but finally we have to leave it at this stage and for other people to try to understand it. Okay. Now, I would like also to address the critical behavior. So this has been measured in some other system. where we were looking for a spinematic phase. That doesn't matter. The issue is that at the quantum critical point, we have investigated much this part by T1 measurements, and then we are looking carefully. We have a good set of experimental data. We're looking carefully for the theoretical description, and we understood what it is all about. Because there is a simple theoretical prediction what the relaxation rate should be as you go that way. And then the experimentalists nicely want to fit that, but it turns out that this does not fit. So we wanted to understand that. So the point is that to describe the fluctuations here, it is theoretically well understood, and you can get the full analytical formulas. So there is a single magnet contribution. This contributes to SZ fluctuation. This is just the excitation across the gap. And you can calculate how it is. You can calculate it exactly, exact function, but not as a function of a gap, but as a function of a chemical potential. Okay? It's the same for the S plus, S minus fluctuations. So this is a second order critical contribution. Theorists have calculated that long time before. This is again analytical functions. It is a little bit complicated, but it's given as such, but it is also a function of the chemical potential. We do not measure chemical potential. We measure the field, and field is the gap. So the good thing is these calculations are for sure good if we take the limit where the gap is much bigger than temperature. Then chemical potential is the gap, and this becomes just a gap, one gap. And in the same limit, these functions just gives you a triple gap. So it's a three-magnon process and gives you a triple gap. So the limit is okay, but what about but in order to get real functions exactly, what we need to calculate is actually chemical potential. So here is the formula. Chemical potential is the gap, but there is a correction due to the interaction. And correction is the number of bosons times the interaction in the bosons. Okay? So the gap is just given the magnetic field. So it's a linear in field. Gap, we measure the field, so we know the gap. That's not a problem. This we know. This is a number, and this we know how to calculate. So when you inject here the formula for the number of bosons, and you take the edge of the boson density is given by the parabolic dispersion. Parabolic dispersion, that's a three-dimensional regime. Here we are at low temperature. Parabolic dispersion gives you a square root dependence as a function of the energy for the density of states. Then this formula is converted to this formula. There is a polylogarithm function of the exponential. These two parameters, u and G naught, are contracted to just a characteristic formula, characteristic temperature. And to get the dependence of mu as a function of delta, it's a numerical solution. You cannot get it analytical. But you can make it. So that's numerical. And you have the mu here divided by temperature as a function of gap. So this is a linear for the zero temperature, and then for the non-zero temperature is not linear here across the critical point. And where the chemical potential goes to zero, that's the transition point. This goes to the transition. So then we take these values, we look at the quantum critical point, and we look how the chemical potential varies with temperature. And what we find actually is that in order to get the convergence of this formula, this is what the theorists calculate. They calculate the low temperature limit of that. Okay, but I didn't look where it is the low temperature limit. So The low temperature limit here, these are the normal experimental temperature. And this is the low temperature limit. A low temperature limit is 4 orders of magnitude below. You cannot go there experimentally. That's impossible. Temperature is too. So the theoretical limit here, limit of that is actually, that's an academic limit. You can calculate it. You cannot experimentally go there. And you can see, if you calculate the slope, this is the limit behavior, and you see that you approach that limit very low. But here is where we have, and the slope of that is very different. Here it's 0.5, here it's 0.3. So the problem about the theoretical description is that low temperature limit is too low temperature. It's inaccessible experimentally. So we know what's wrong about it. It's not that bad if we calculate not just the chemical potential, but the fluctuations as a function of temperature. It's pretty power law with the small fluctuation. The exponent is slightly varying. So this is a logarithmic derivative. So this is the exponent. So the low temperature limit, the famous low temperature theoretical limit, 3/4 exponent, it's for the temperatures below 10 to minus 8 as compared to the normal temperature. So you understand that this is not accessible. But when we go here, the exponent is still close to that value, but the point is that we do not get only the second order contribution, but we also get a first order contribution. And we measure the mixture of the two. So actually, when we measure here an exponent, here it's 1, which is close to this value, but it's not a universal exponent. Universal exponent is here at the low temperature. This is non-universal exponent. So, okay, we do measure theoretical value, but non-universal one, which means that we never measure 3/4. We measure something there, but not the 3/4. Now, if we go at higher temperature, so this regime corresponds of these temperatures. So we are below the maximum transition temperature. So if we go high above, so this is calculated by a 3-dimensional system. If you go high above, the system is rather low dimensional. And so this is changing the behavior. So above, at higher temperature, we get high temperature, low dimensional behavior. And then the issue is, okay, if I go to very low temperature, will this improve the situation? And then we define, okay, but it does not improve. We do not get closer to that. We get, instead of 1, we get 3. We get something totally different. So what's the point? But the point is very simple, in fact. This behavior we get here for these points. And these points are too close to the phase transition. So theoretically, at the phase boundary, the spin fluctuations should diverge. But in the real life, there is always a cutoff, or there is inhomogeneity. So the infinite peak is always spread for some reasons. So, and that means that this peak has a certain width. And if we are too close, we measure the value at the peak. We don't measure the value which is nearby and the peak is infinitely sharp, but we measure the value of the peak. And indeed, if we try to measure the value we follow the phase transition and measure the relaxation rate as a function of temperature. And we see that here, this cube behavior goes to 0.3 degrees. But if we measure here, but if we measure like that, we have the same cube behavior which extends up to 2 Kelvin. So we know that at the low temperature, what we measure is the value at the phase boundary. And we know that this value is not universal because it comes from some sort of a cutoff. either of inhomogeneity, which spreads the peak, or of some physical cutoff. So here we were speculating a little bit that at the phase boundary, the density of the hardcore boson is theoretically expected to depend as a temperature to the 3/2 exponent. So what we measure is exponent 3, which is 2 times that. So what we measure experimentally, phenomenologically, is that T1 here is proportional to what is supposed to be the critical boson density squared. Critical means the boson density at the transition. So we speculated perhaps it's some sort of bosonic Corringa law, but that's a speculation. The point is that when we measure this, we do not get that. We get critical value, which is non-universal because it is at higher temperature, and at a lower temperature we are too close to the phase boundary, and we get actually the behavior of the phase boundary, which is non-universal again. So we know the fluctuations. Okay, so that brings us to the summary. There is one point that I didn't say, that why I stick so much to the T1. T1 is a very robust observable for the NMR. So the interpretation is straightforward. There are no subtractions. There are no funny things about that. So practically, it's a very robust observable. The main message is that T1 data provide effective dimensionality. We see the peak at the second order phase transition. We know whether the system is quasi 1D, quasi 2D, or quasi 3D. Okay? We have a full description in a quasi 1D system. If we want to describe the fluctuations above the ordered phase, this regime, we need to add the RPA corrections to the 1D description, and then it works very nice. It works even for 3D coupling, which is of the order 10% of the main coupling. And if we have a good fit on this NMR data, we know the K value, and that means that we know the interaction parameter. Even if we do not know the microscopic details of the system, we know what the system is. Well, the system is much more delicate in a quasi two-dimensional system. We have measurement in the NMR. We have done a quantum Monte Carlo description. Quantum Monte Carlo recovers the critical temperature, TNL temperature. We recover the Kosterlitz-Towles temperature. We recover the Q dependence of the fluctuations, and we know everything where the correlation length to the description is applicable to the real 3D case. And we know that for the quantum critical points, NMR and quantum Monte Carlo agree. And we know that so here the NMR. If we are here, we have a problem. NMR gives the exponent of 1.2, and the quantum Monte Carlo is lower exponent, and we need, so the future generations will perhaps know what it is. Okay, and finally, if we measure right here, so this is for the 2D regime, and if we measure here for the 3D regime, we know that we do not have a theoretical prediction because it corresponds to temperatures which are much too low. But what we see, starting from 0, we have first we measure at the phase boundary because we are too close to the phase boundary. Then we measure the critical 3D critical behavior, but which is not universal. And then at higher temperature, we measure the high temperature and low D effects. So we have a pretty complete view on the spin fluctuations on gapless spin systems, and which is pretty much universal. And with that, I thank you for your attention.
Okay.